Okay, so today we're going to talk about what I like to call the constitutive relationship, mostly because it sounds really cool. If you want to be real basic, this is the stress-strain relationship. But when you call it the constitutive relationship, you sound sophisticated, like you've been to grad school. So, but at the end of the day, all it's doing is relating the stress in a material to the strain that it experiences. So we can look at this in terms of normal or shear, but we're going to start our discussion with normal. So we're talking about normal stress, and we're talking about normal strain. And then this constitutive relationship relates those two together, and it's going to be unique to the material. So steel will have a different relationship than concrete, which will have a different relationship than, say, timber, which is different than polycarbonate. Right? Every material will have a different relationship. One of my students sent me this video a couple weeks ago. So after you graduate and you go do really cool things with your life, if you want to send me stuff that helps me be a better professor, I would greatly appreciate that. So he sent me this video. This is a very large piece of rebar. I want to say he said a number 11. So first of all, rebar is the stuff that we put inside concrete to give it tensile capacity. And it's a steel material that has, you can kind of see it has like roughness on the sides. It's not a smooth bar. That roughness helps it to interact with the concrete to get kind of grabbed by the concrete so that it doesn't slide. And they have to test it to make sure it has the right tensile properties. And the size of the bar is measured in 1/8 of inches. So if you have a number 8 bar, that means it's 8/8 of an inch, which is 1 inch. So if you have number 11 bar, I believe that would be 11/8 of an inch, so a little bit higher than an inch. All right, so this is the video. Let's watch this. Oh, I gotta get my clicker. So also note that there are two, I think, is it going? There are two white lines drawn on it that are moving. There we go. They're moving away from each other. Yep. You want to watch it one more time? One more time. Okay, so in the beginning, it doesn't look like it's moving much at all, but then you start, and so that would be like our elastic region where it doesn't have very much, we're applying more load, but it doesn't have a lot of displacement, and then it starts to have a lot of displacement. So you can see there a lot of elongation, and eventually it ruptures. So we're going to mathematically describe what's happening there. What they just did is what we call material testing. You take a specimen, you put it on the machine, you pull on it. That was a piece of rebar, which is specifically for the purposes of ensuring that that rebar is adequate for the job, make sure it was manufactured properly. But we also test specimens to find out material properties. And so this is a standard tensile testing specimen. Has a 1/2 inch diameter, round, and on the ends it has these threads so that we can thread it into the machine. So that is what I have drawn here. And so you can imagine that there should be threads there. And then in the middle, we have 2 marks. And they're separated by a distance called the gauge length. And that gauge length is typically 2 inches. And in that section, it's a reduced cross-section compared to the threads because we want that middle section to be the smallest cross-sectional area. And when we pull on this, we're going to be measuring macroscopic quantities. So directly from this test, all we can get are average values, right? We're measuring the total load applied, the total distance that it elongates, the initial length, I'm sorry, that D is the diameter. The diameter of the member, we have the initial length and then the amount that it elongates, and then we have the change in diameter. But we only know that change in diameter at the end of the test. We don't measure it in real time as the test is going. And so in order for this to be useful to us, we want a uniform stress state. Because if we're only dealing with average values, but what really matters are exact values, if we have a uniform stress state, then those are one and the same. And so that is the intention of designing the specimen the way it's designed. We get more or less a uniform stress state, and it's experiencing what we call uniaxial tension, which means there is a force in only one axial direction. So we have force acting like this and like that. There shouldn't be any force in any of the either two directions. So what that means is that the normal stress in that direction is non-zero. You have some force divided by the cross-sectional area, but all other components are equal to 0. There's no other force vectors, so therefore there's no other stresses. And to calculate the normal stress, we take that force that's applied and divide by the area of the specimen. For a standard specimen, that would be pi d squared over 4 because it's a round cross-section. And to calculate the axial strain, the normal strain, we have the change in length divided by the initial length. Give me just a second. I want to pull something else up. Any questions so far while I'm doing this?
That's the cross-sectional area on the bottom? Okay.
Yes. Okay. Okay, so if we're plotting, say, stress versus strain, which is how we do our strain on the horizontal axis and our stress on the vertical axis. If we have a material that's such as glass or ceramic, it might have a curve that looks something like that, and then it might break where I have that X. So that would be like glass or ceramic. We might have a material more like steel or a ductile steel that would behave more like that. And you might have some other metals that behave more like that, say like aluminum. Now it's important for you to recognize that, and we'll draw a better picture of the steel curve later, but there's kind of a characteristic steel curve that we always talk about, and especially so in civil engineering. But steel is a man-made material that can have different compositions. And so there's not just one steel value or one steel constitutive relationship. Depending on the type of steel you're dealing with, you'll get a slightly different relationship. And same thing actually happens with aluminum. So we're typically not dealing with a pure, aluminum element. It's some kind of alloy. And so some of the characteristics will differ. So like, for example, the amount of strain before it ruptures. In some cases, steel might be more strain. In other cases, aluminum might be more strain. It just depends on the two particular metals that you're comparing, or those two compositions that you're comparing. So ductile materials will elongate more before fracture. So if you get a lot of elongation, we say that's more ductile than a material that had just a little bit of elongation. So in this previous example, which of those would you say is more ductile? Steel, or maybe even the aluminum, whereas the glass or ceramic is less ductile? And we can quantify based on the percent elongation whether a material is classified as brittle or ductile. So ductility is a spectrum. It's a spectrum where you can have increasing levels of ductility, but there is also this kind of classification system where if you fracture prior to 5% elongation, you call that a brittle material. But even within brittle materials, one can be more ductile than the other. Or within ductile materials, one can be more brittle than the other. So to calculate these percent elongations, we take the final length minus the initial length, divided by the initial length, and then multiply by 100. You can do a very similar calculation with the area. So you can take your final area. After you break your specimen, you can measure that final area, subtract the initial area, divide by the initial area, multiply by 100. And then that will give us our percent area reduction. And let's see, I have written here, sum of cross-section planar axial strains. Oh, that's right. Remember last time we talked about change in area divided by area? We said,
Oh yeah, there's one X.
yeah, delta A over A. We'll say epsilon Y plus epsilon Z in this case, because those are the two planar directions. So if you knew the equation for the strain in the perpendicular direction, you could add those two equations and get this. So note we only have stress in one direction, but we have strain in all three directions. And why? Do you know why that is? We'll talk about it later, but have you heard of the Poisson effect? So the Poisson effect is the idea that as a material elongates or contracts in one direction, the cross-sectional directions will be affected. So if you elongate a material in, say, the X direction, it's going to contract in the Y and the Z. You can think of like bubble gum. Have you had kind of a piece of bubble gum or the silly putty where you extend it out like this and then you see it shrink in? That's Poisson effect. So even though you have stress only in one direction, you have strain in all three. All right, so this is our steel, our kind of classic steel stress strain curve. Stress, normal stress is on the Y, normal strain is on the X axes. And then it starts linear, has kind of a little trough, and then goes back up. This right here is what we call the upper yield limit. So the top of that first crest. The lower yield limit is the bottom of this trough. And the lower yield limit is what we use as our sigma Y value, our yield. So note that that's a capital Y, not a lowercase y. So I'm not talking about the normal stress in the Y direction. I am instead talking about the normal stress at which the material starts yielding. And that's equivalent to your lower yield limit. It's also essentially where that material stops being linear. Okay, so below that value, you have a linear relationship for steel between stress and strain. And after that, let's just say after that, you get significantly more deformation with the increase in stress. And that's what we consider yielding.
So sigma y is lower than yield limit?
Yes. And in some cases, in some materials, you don't have this nice little trough and then crest. And so there is only, say, one value. There's not the upper and the lower. But if you have both, then you use that lower yield limit as your capacity for yielding. So when we're increasing our stress, that corresponds to loading. Right? Anytime you have stress increase, that means the load is increasing. And then decreasing would indicate that you have unloading occurring, right? Because your force is going down. And then we have an increase in strain that would indicate that our material is elongating. So as you move to the right on this diagram, your material is getting longer. And if you ever saw your strain decreasing, that would indicate that you were contracting. Now in this particular plot, this represents pulling on a material and just continuing to pull until it eventually ruptures. So you don't see any contracting, right? It's elongating the whole time. But you could conceivably pull on a material and at a certain point stop and then relieve that force, go back to zero and then compress it. And that's what we call cyclic loading. So you can do that where you pull and push and pull and push, and then you would see this curve going back towards the left when it's contracting. There are a number of important regions on this graph. The first is the elastic region. So this here is the elastic region. Okay, so the elastic region is that area under which the material is behaving elastically, and I'm going to clarify what I mean for you when I say elastic. Maybe I'll do that right now. So elastic means that when we remove the load, the material goes back to its initial position. So we apply some load, the material deforms. If I let go of that load, it goes back to its initial condition. That's elastic. So anytime we're in that region and we unload, it's going to follow that same curve back down. At the edge of that elastic region is our elastic strain. So just like we have an elastic yield, so we have our yield stress, we can have what's called a yield strain. That's essentially the strain that occurs when you reach your yield stress. Next, our material starts yielding, and I would say that would be this region here. Really anything to the right of our elastic region is yielding, but we have more specific names for those regions. So this is the beginning of our yielding. Yielding indicates that you have significant increase in deformation as you have small increases in your load. So in the beginning, the slope is quite steep. You have an increase in your load, and you get only a very slight increase in your displacement. Once you reach yielding, it starts to be more deformation, and some of that deformation is going to be permanent. So that characterizes yielding.
So with that yielding region, would that rightmost line be at that dip?
Yeah, roughly. Yeah, yes, it is at the dip, yes. because the next region is what we call strain hardening. And that is when you start getting an increase in your stress again. And that doesn't happen for all materials. Some materials will not have a dip and then go back up. Some materials will kind of just plateau after they reach their yield. But for the structural steel, we see this dip and then we get strain hardening. We'll talk about what that is in just a second. And then after we reach that top level, which is what we call our ultimate stress. So this up here would be sigma U. It's your ultimate value of stress. Then we start to see the stress decrease. And that's what we call necking. Because in this region, you start to see a significant shrinking of your cross section as your stress is coming back down. All right. So let's talk about some of these things that I just mentioned, starting with strain hardening. Why does a material strain harden? So if I have this material, if you look at the, say, microscopic lattice structure, so how these the molecular structure of the material, let's just say that they're arranged like this. Okay. And as we pull on this material, these molecules will start to move farther apart or they'll have to stretch. But at a certain point, they're no longer going to be aligned in this nice lattice. So what's going to start happening is you might have elements that are moving past each other. So they move out of their original molecular form and they actually slide past each other. And that's what is happening at the molecular level when you have strain or when you have yielding. And that's why they're not going to go back to their original position all the way. And so that's why you have that permanent deformation. They've actually slid past each other and you can't get them to go back to their initial location by just unloading them. And eventually, as they're sliding past each other, they will kind of re-engage. So I'm not saying this is exactly what happens, but if you kind of imagine them now, instead of being in rows and columns, say they kind of slip into where they're each in the diagonal, they've re-engaged in a new location. And then when you pull on it, they're not just sliding past each other. They're starting to latch on and give you more resistance again. And so that's that strain hardening. But at a certain point, you start to see this necking, where now we're going the other way and we're decreasing our stress. So what do you think that's all about?
It's because all the strain is going to narrowing the area.
Yes, it has to do with that narrowing of the area, definitely.
So just removing the loads, there's less strain, less stress, so technically you're just not elongating anymore, it's contracting. Going back to its original shape.
Not its original shape, because the length isn't contracting, the length is still extending, but what's happening is you're getting a lot of, at a certain location on the cross section, or along the length, you're starting to get a lot of contraction of that diameter. So you need to recognize that what we've been talking about this far is engineering stress. But there's something called true stress, and these are not equal. So if you have friends who are studying more like material science, and they're less concerned about our engineering applications and more concerned about how the material itself performs, they would be interested in true stress. What is actually happening to that material? Whereas we're more interested in the system and how the system performs. And so if we can predict system behavior, we don't really care what's happening at the molecular level of this material. And so that's our engineering stress. It's practical and useful to calculate stresses using your initial area, correct? You specified that the part had a certain diameter, they installed it. After that, it got loaded. You have no idea what the cross-section is as it's being loaded, but you do know what it was when it was placed into service. And so that's useful for us as engineers because we don't have a lot of measurements in the field measuring the dimension at any one time. We use engineering stress in which our cross-section always remains the same. So when we say stress equals P over A, this A is always the initial stress. And when we say that strain equals delta L over L, this is always the initial, and this is always the total. So it's how much has it deformed since we started the test, divided by the length it was when we started the test. Now, yes?
So for the necking, it's technically the strain is going down, but the stress is going down, but the strain is still going up.
Strain is getting larger because the delta L is continuing to increasing.
Even though stress is going down, right?
Yes.
Unloading.
Yes. Yes. And we see that stress coming down. In our calculation, the area stays the same, which means that the load P is going down, right? That if A is staying constant, but stress is going down, the only thing that could be happening is P has to be going down. The load is going down. But if we were to talk about this in terms of true stress and strain, and we calculate sigma T for true, then this A is instantaneous. Now, when we divide by the area, where each time interval, say we're taking measurements at each 1/10 of a second, for each 1/10 of a second that we proceed along this testing protocol, our area is getting smaller and smaller. So we're always dividing by a smaller area. Now that load might also be getting smaller, but the area is getting smaller at a quicker, does that make sense? They're getting smaller such that the resulting stress is actually increasing up until failure. So if I told you that this was our engineering, the true value starts out the same, and then you might have some slight divergence, but, oh, that's a terrible picture. I'm a one-trick pony. Oh, I got rid of both of them, great. I've got like muscle memory for that engineering one, but let's do this true one. There, that's better. So they start out the same, but as you start to yield, you'll start to see a little bit of divergence. And then when the engineering strain or stress comes down, you see that true stress continue up. So that's true. And so really what's happening is that the material itself continues to carry more and more stress until eventually it just can't take it anymore and it ruptures. Yes. Yeah, and so if you were to calculate it with that instantaneous area, right, if the area is smaller, it has more stress, but it can do that at a smaller load level, And so it looks like the stress is decreasing when we calculate it from an engineering perspective. Right. But what's really happening is just your area is getting smaller and smaller. And so the amount of force that it requires to have a continually increasing stress is actually a decreasing force. And we have, see, we can calculate, let's also calculate the engineering strain. Or sorry, the true strain. True strain is the sum of delta L over L, where the delta L is just the last increment. And then L is instantaneous. So for each loading step, each tenth of a second, you would calculate the amount of change in length over that tenth of a second and divide it by the instantaneous length. So say the length at the beginning of that tenth of a second. And then you sum them all up all the way through the loading protocol to get your total strain. So it's a lot more difficult computationally. And so as engineers, we don't do that, but that's the true value of strain. And if you do this, this is equal to the integral from your initial length to your final length of dl over L, which is also mathematically equal to the ln of L minus the ln of L naught. Which we can simplify further to be the ln of L over L naught and that equals the ln of L naught plus delta L over L naught. And that numerator, or not necessarily numerator, sorry, that fraction, L naught plus delta L, so initial length plus change in length divided by initial length, that can be simplified as 1 plus the strain, right? Because L naught over L naught is 1, and delta L over L is strain. So this then becomes ln of 1 plus the engineering strain. So we can go back and forth between the true and the engineering. If we need the true, we can calculate the engineering value easily based on the information we record from the lab, and then we can calculate the true value of strain. Oh, you know what, I think we're good, yeah. We can calculate the true value of strain from that engineering value. Similarly, we can calculate the true stress. So if we say that this volume initially is A naught L naught, that's the volume of the material, and at any time that's going to be equal to the area times the length, so we're going to keep a same volume. We can rearrange that so that it's A naught over A equal to L naught over L. Oops, I think I made those backwards, didn't I? L over L naught, right? Okay. All right, and L over L naught is the same as initial length plus delta length, right? L is just the length at any time. So it's what you started with plus what you've added. So this also is equal to 1 plus strain. If I calculate my true stress, and I want to say that that true stress has to be equal to P over A, where A is instantaneous. If I multiply this by A naught over A naught, I don't affect the equation, correct? Cool. But doing so gives me P over A naught, which is equal to what? Sigma, that's my engineering stress. And it also gives me A naught over A, which I just said was equal to 1 plus the strain. So my engineering stress is equal to my true stress is equal to my engineering stress times 1 plus the strain. So in terms of what you're doing at the undergraduate level, you probably won't really need the true stress and strain, but it's good that you know what it is because that's how the material actually behaves. And if you end up in a situation where you're going to, say, be modeling a material using finite element analysis, and you're inputting the material properties, or rather the constitutive relationship, you need to use the true, because the finite element model, which is analyzing the material, is concerned with what's actually happening in the material, right? It's not concerned with the system, it's concerned with the material itself. And so it needs to know the true values. But for us, all we really want to know is, all of our framework for design is based on this average stress, essentially. What is the normal stress in terms of that initial area? And so we don't need to know the true stress in most applications.
So technically, you like, let's say, graduate now with a bachelor's, you go to work, you do true, or even at that level, you're doing just engineering now?
Which field are you in?
Civil.
Civil? Then no, on a daily basis, you would not be dealing with true stresses or strains. No. Yeah, you would, all of the design codes for civil engineering are based in terms of engineering stresses and strains. All right, so I'm going to back up a slide because we skipped over something called the offset method. So when we have a material and the stress strain curve looks something like this, it's a little bit difficult to pinpoint when that material stopped being elastic. There's not some definite change in the response. And so this offset method tells us to draw a line that's parallel to the initial slope. So if this is our initial slope, we would draw a parallel line such that that parallel line starts at a strain value of 0.002. So sometimes you'll hear this referred to as the 0.002 offset method. So you start at 0.002 and then you go with a slope equal to the initial slope, and where that intersects with the curve is what you would say is your yield stress. And I probably drew it farther to the right than would be realistic for this curve, but the point still applies.
That would be the Young's modulus, right? The slope.
Yes.
Is that subscript capital Y?
Yes. Yeah. Other questions?
So this offset method is just deciding the sigma y.
Yes. This offset method is to get your yield stress when it's not visually apparent. Yeah, you want this one?
The one next.
That one. All right, so I've been using the word elastic without really talking about it. We briefly talked about it. So to reiterate, elasticity is deformation being recovered when the material is unloaded. So I apply a load, I get deformation, I remove that load, the deformation is removed. That would be an elastic situation. No permanent deformation. And what that means is that your instantaneous stress and strain are related. If I tell you the value of your stress, you can tell me the value of the strain. And all you need to know is the current values. You don't need to know what's happened to the material in the past. Whereas once we move past elasticity into nonlinear behavior, or let me be very careful, that's a bad thing to say. Once we move into plastic behavior, you now need to know the time history. You need to know how much it's been in stress in the past in order to tell me what the current strain would be, because it will have some permanent deformation. And it's very easy to mistake elasticity with linearity. And in fact, if you notice, I have even just done that. Linearity is something entirely different than elasticity, but in most practical purposes, we see them going together. So linearity means that your stress and your strain are linearly related. So you would have that material, and what's your name again?
Josh.
Josh. You were the one who pointed out the Young's modulus? No. Blake pointed out the Young's modulus. All right, so the slope of this linear segment is what we give a capital E to, so it's signified by a capital E, and that's the modulus of elasticity, also referred to as Young's modulus. Most commonly, our elastic region is linear. So linear elasticity, which means two different things: linear, indicating that stress and strain have a linear relationship, and elasticity, indicating that when you unload it, it's going to follow back down along that same path. This is our most common. However, it is possible to have a material that is non-linear elastic. So that means your material might look like that. So concrete is probably the most common material that we deal with that is non-linear elastic. And in this case, you have an initial. You still have a Young's modulus. You still have that value of elasticity, and Young's modulus in particular is what we refer to as that initial slope. So that initial slope has meaning for concrete, but very quickly as you go along the constitutive relationship, it starts changing slope. You know, it's kind of more of an arc than a line. And so when they're linearly related, we have this equation that says that stress is the modulus of elasticity times the strain. So we will use this equation. This is expressed in uniaxial loading, but or sorry, this is kind of a one-dimensional. This will become a more complicated equation, but at the end of the day, the basic form of this equation is that you have some strain multiplied by your modulus of elasticity because it's a linear relationship that gives you stress.
So that only applies to that linear class.
The form of it being written like this only applies. Let me rephrase. What you just asked, the answer is yes. This equation only applies to linear elasticity. And then what I started to answer, which was not your question, is does that only apply to uniaxial loading, which is the one direction of loading? And the answer to that is yes. We have a more complicated form of this equation for when we have loading in multiple directions.
And the elasticity, those apply for both, right? Linear and nonlinear.
Yes. Yes. So for example, we could load this material and it would follow this curve up till this point. And then if we unloaded it, it would follow back down. And if you unloaded it all the way, it would go back down to 0. If you only unloaded it partially, it would end up at this point. Right. But once you get to plastic behavior, that's not the case. And we're going to talk, I think that's what next lecture is about, is looking at plastic behavior. So let's do a quick example. This is stress, this is strain. And let's say that our cross-sectional area is pi r squared, so it's a circular area where r is equal to 1/4 inch. So that corresponds to this typical tensile specimen where it has a radius of 1/4 inch or a diameter of 1/2 inch. And my question to you is compute the force, the axial force that occurs at, we'll say this point here. So that's just kind of an arbitrarily picked point. And I'm going to say that that stress at that point is 60 KSI. So if it's a 60 KSI stress, what is the force, the tensile force? And the strain, let's say, is 0.11. So what is change in length? So why don't you take a few minutes to think about that, work with somebody, and then you can turn in your papers together. Okay, how did you calculate the force? You take the stress and what do you do to it? Okay, so you had 60 KSI multiplied by pi 1/4 squared. And what did you get?
11.78.
All right, 11.78 kips. So that's 11,000 pounds, thereabouts. All right, how do you calculate the amount of change in length? Okay, so strain is equal to, it's not directly equal to change in length, right? Okay, so delta L over L is equal to strain, which means delta L is equal to strain times length. And if your strain is 0.11 and your initial length was 2, you get 0.22 inches of strain.